So I'm going to talk today about my work developing a concept inventory for CS2, which is what we commonly call the second class in the computer science curriculum. Now before I begin, I want to get a kind of an idea of if you've heard of either of these things. So if you've heard of a concept inventory before, can you raise your hand? Oh, awesome. So almost all of you, that's amazing. And if you've ever taken any computer science at all, can you raise your hand? Cool, awesome. Okay, so I'm going to give a brief introduction to concept inventory. It sounds like it'll mostly be stuff all of you are familiar with, and then I'm going to get into the computer science side. And if you have any questions at any time, just raise your hand, especially about the computer science stuff. I'm going to do my best to make it understandable, but I'm used to talking to engineers, so if it doesn't make sense, let me know and I'll break it down. So in CS education in general, in education research in general, it's kind of an iterative process. We start with whatever the people before us were doing, we come up with some improvement, we evaluate student learning after we've done our improvement, and we try to determine if the improvements resulted in improved learning. And this is really the goal. Of course, all of you who are actually doing it know that in general it's a lot messier than that, and especially that this piece here is incredibly difficult, right? It's really hard to tell, did students actually learn more because I did this than if I did this other thing? And that piece right there is really where our concept inventory data comes. The goal of a concept inventory is to evaluate student learning and eventually, especially to evaluate it under different pedagogical interventions. So in general, when we assess a classroom, we have some goals for assessment in general. First of all, we'd like it to be easy to assess our students. We want it to fit into our classes. We don't want to spend more time assessing our students than we actually spend teaching them. We want it to be technical. We want it to be highly connected to the core concepts of the class, and we want the students to be able to demonstrate their technical knowledge in the subject area. We want it to be comprehensive, so we want to cover most or all of the material that we taught in the course. And then we want it lastly to be comparable, so we want to be able to compare our measurements to other courses, to other instructions, and to other pedagogical techniques and interventions. And so when we look at how we assess courses and learning in general, we have homeworks and lab assignments, which are practical. Students do them on their own time. They're easy to assign. And they're also technical. They're very enmeshed in the concrete details of what the students are learning in our courses. We have student surveys, which are practical and comparable. An easy way to tell if students liked a thing is just to survey them, and it's pretty easy to give them kind of a bunch of Likert scales and compare to other things, but this isn't technical, right? We're not really testing students when we give them surveys. In fact, the surveys were mostly finding out, did students like a thing rather than did they learn more from a thing. We have midterms and final exams, which are technical and comprehensive and practical, but are not comparable, right? My final exam may not cover the same things that your final exam does, even if it's for the exact same course. So what we're missing here is something that is both technical and comparable, something that will assess student learning, but allow me to compare how much did students learn in my course compared to how much did students learn in another course that covers more or less the same material. And so that's the goal of the concept inventory. We want something that'll cover course concepts, so it's technical, it's very connected to what students are supposed to be learning in the class. It's practical, so it's easy to give. It's not going to be a burden on someone to give it because we want a lot of data. The goal of this is to collect data on how well students learn under different pedagogical treatments, and so it needs to be easy for people to give to their classes or else no one's going to do it. And lastly, we really want this to be comparable against every sort of implementation of a certain course. So if we have one for CS2, we want it to be comparable across every CS2 course at every institution. So concept inventories in general are a short, standardized exam. So they're not comprehensive, they're looking at high-level conceptual takeaways. So we're really getting away from can students write a formula and do the math and get the answer, and more towards do students fundamentally understand the core concepts of the material, and do they kind of understand how the world works based on this? The goal is to reveal systematic misconceptions. So is there something that my students commonly get wrong that also your students commonly get wrong? And can we kind of teach them to avoid this misconception? Not always, but generally they're multiple choice questions. The one that I'm developing is multiple choice, and this really gets at that practical aspect. Making it multiple choice makes it easy for an instructor to grade it, right? It means you don't have to go in with a rubric and do a lot of stuff. And frequently they're deployed both before and after courses, although this kind of depends on subject matter. So in computer science, we don't usually deploy them before and after, because computer science involves a lot of language that students don't really understand before the course. So we've established in a lot of computer science subjects that if we give them before the course, they just kind of pick things at random and it is not actually comparable. So the goal here is that we can compare student learning across instructor, across institution, across curriculum to some extent, and most importantly, across pedagogical practice, right? What I'm really interested in is how can we best teach computer science, and as a side effect of this, I've become interested in computer science because, become interested in concept inventories because I want to be able to measure, am I doing a good job of teaching computer science? If I do this in my classroom, does it actually make my students learn more than if I do some other thing? So that's really the goal. And concept inventories are not a new idea. They've been around for a long time, especially in physics. The force concept inventory was sort of the first and definitely the most famous of the concept inventories. All of you who know about concept inventories probably have heard of this before. And it really established that students could do really well on these traditional exams and still not change their fundamental concept of the world or how they really understood how these concepts work. So they could do equations, they could memorize things, they could do math, but they still didn't understand the fundamental ideas of what physics means for the world, right? So 80% of students could state Newton's third law at the beginning of the course. FCI data showed that less than 15% of them really understood it at the end of the course. And this really fundamentally changed physics education. As a computer scientist, I'm deeply jealous of physics education because they are so far ahead of us. Like, this made physics teachers really think we have to change what they're doing. Peer instruction really came out of this. A lot of amazing stuff came out of the results of this, which really shook the physics education community and showed them, you know, even our students who get A's are not learning and conceptualizing the way we want them to. And the FCI inspired concept inventories in a whole bunch of other fields. So a ton of STEM fields have these now. There's a list of them right there. They're all over the place. However, in CS, there are almost no validated concept inventories. In fact, there are two. There's one for CS1 that just came out last year, and there's one for digital logic that's kind of on the borderline of CS and electrical engineering that's been around for a while. So there's very few concept inventories that have actually been rigorously validated through the interview and statistic process. But a bunch of them are currently under development. There's one for algorithms that's currently being developed. There's one for recursion. And then we are currently developing one for computer science, for CS2. So I am now going to talk a little bit about what the steps are to develop a concept inventory. One of the reasons there's not a lot of concept inventories is there are a ton of work to develop. If you feel definitely more work than we realized when we wrote the NSF grant to develop this one. So our first step here is really that we have to figure out what actually happens in a course. What are the actual topics and concepts that are being covered in a particular course? And so to do that, There's a bunch of things we can do. We can interview instructors, we can read syllabi for a course, we can read final exams. People also frequently read textbooks, and this kind of just gives us a general idea of what are considered the core concepts, and bigger than the core concepts, even the core topics for a course. And it turned out that in our work in CS2, this was a lot less clear than we expected, and I'll talk about that in just a little bit. After we know the core topics, we need to develop open-ended questions that are related to the learning goals and topics for the course. And you sort of aim for multiple questions on each of the learning goals just to make sure that we can sort of validate those questions against each other, right? We can see, okay, if a student does well on this question, do they also do well on the other related question? Or is something wonky with my question that they're doing much better on this one than this one? So in our development, in trying to come up with these questions, we were very lucky in that one of our collaborators on this project is someone who has been teaching CS2 at UC Berkeley for literally 20 years. And so he had a huge corpus of already developed CS2 final exams that we could go through and kind of see, okay, which of these questions are connected to our learning goals. And so we started kind of with that set of questions and then modified and developed them as we went through this development process. So after we developed these open-ended questions, we needed to develop multiple choice distractors as well as the right answer for these questions. And our goal for these distractors was to have them connected to actual student misconceptions. And so in order to develop these distractor answers, we did two things. We first interviewed students while they were taking the test, while they were doing what's called think aloud. So they were taking the test and they were just narrating aloud what they were thinking as they took it. The other thing we did is we gave large-scale open-ended versions of our test questions and we coded our answers. So we gave a couple, we bugged our friends who teach CS2 and we said, hey, do you want us to give a practice exam for you? Do you want us to take over your lab session and give your students some test prep? And so we gave a couple of these in different classes. We ended up with several hundred versions of the tests that students had tested. And so then we went through the answers and we categorized the answers as, okay, this set of answers seems to have this misconception, this set seems to have this misconception, and so on. And so that's really how we develop kind of the distractor wrong answers for our test questions. And then the sort of last thing we do once we finally have developed this test is validation. And there's really two different ways we validate the test. The first is just having students take it and again do think alouds while they're taking it so we can see, okay, if they choose the correct answer, are they choosing it for the right reasons, or are they choosing it because it's the longest answer? I was doing a think aloud with a student and they chose the right answer, and I'm 90% sure they didn't actually know which data structure it was. They were just like, oh, that has the word array in it, so I'm going with this one, right? So it's very useful to do this think aloud process because it tells us, okay, why are students choosing these answers? And likewise, a lot of these think alouds ended up kind of debugging our tests a lot. We found a lot of errors, kind of misspellings, words and techniques students weren't familiar with, and so on. As part of this, also, we were doing this at UC San Diego, and we discovered there's actually a concept they don't teach there, that everyone in CS1 assumed they taught in CS2, and everyone in CS2 assumed they taught in CS1, so our concept inventory has already caught something at UCSD. And then lastly, once we have a final version that's gone through this process, we want to statistically validate the concept inventory. There's a lot of different ways we can do this, sort of with some of which work better than others. Kind of the best thing to do is if there's another validated concept inventory on the same topic, you can compare how students do on your test to that test. Unfortunately, if there's another validated one on your topic, maybe you don't need one, right? So that depends on there already being one. You can compare how students do to final exam results. There, again, the correlation tells you something. It's not perfect because the whole point is that students can do well on final exams and still do poorly on the concept inventory. Lastly, you can compare how students do on one subpart of the CI to other subparts of the CI. You can use a statistical measure for that. Again, that's not perfect either because you're testing different concepts. Students are maybe not going to do the same level of well on the whole test because they might do better on one concept than another concept. But you want to do some kind of statistical validation between a couple of these things. You can get a pretty good idea of how your students are doing. So that's what concept inventories are. Now I'm going to explain to you what CS2 is. So this is loosely defined as the second course in the CS curriculum. It's kind of the first course where we get away from programming. So usually in CS1 we're teaching them this is how you program, right? This is how you write code. CS2 is the first course where we get a little more abstract. We stop just talking about code. We start talking about kind of the fundamental concepts behind code. What does computer science really mean? How do we represent data? So CS2 is generally about data representation in computer science. And again, it's the first course where you get a little bit theoretical. It's also frequently a bottleneck for more advanced topics. A lot of CS curriculums look like you take CS1, you take CS2, and then after that there's 3 or 4 classes you can take, and then after that you really get access to the rest of the curriculum. It usually covers object-oriented programming and or data structures, and I'm going to talk a lot about this piece in just a second. So our first goal here was just identifying, okay, what topics are there in CS2, right? What do people cover in their CS2 course? And we first came up with this list of 6 really sort of high-level topics, sort of what is being covered there. In order to do this, we interviewed a panel of experts that I'll talk about in just a second. We also read both the syllabi and the final exams from their CS2 courses. Our theory was the syllabi tells us what they want to cover, the final exam tells us what they actually cover, right? The syllabi is sort of an aspirational document. The syllabus is what they actually expected students to learn. And so we found this list of 6 topics that really are not, that are loosely related. And it turned out that almost no CS2 courses covered all of these, but all of them covered some subset of these. And I'm going to talk a lot more about that. But the basic things that these classes covered, they covered object-oriented programming. Object-oriented programming is a sort of programming paradigm. That's how you design programs. So it's kind of how do you group things together, how do you group functionality together, and so on. They talked about basic data structures, which is sort of the introduction to how you represent data. So if you have, say, a bunch of numbers, how do you organize those numbers? How do you represent them in the memory of the computer, and so forth? They covered recursion, which is more or less having a program call itself, which sounds kind of easy, but is actually very, very tricky for students, it turned out. And then some of them cover sorting. So if we have a list of numbers that's in any order, how do we get them ordered from smallest to largest or largest to smallest? It turns out in computer science there's actually a bunch of different ways you can do that, and how you do that sort of gets you at some fundamental problems of computer science. A big CS2 topic was algorithm analysis, which we also call runtime analysis. Algorithm analysis is more or less just the theoretical idea of how do we tell how fast a program will be, and it's sort of how do we mathematically analyze the speed of a program. So it's not just we run the program and we see how long it goes, it's as our input gets bigger, how will our program get slower, right? Will it get drastically slower as we add more input? Will it not get slower at all? And so forth. And then lastly, some of these courses covered advanced data structures, which was just more complicated ways to represent data in the computer. So I told you we got all of this from our panel of experts. A little about our panel of experts. This was a bunch of CS2 instructors. We had 10 experts, although we lost some of them over time. We paid them a small stipend in exchange for sending them surveys and interviewing them and getting them to give us their exams and so forth. All of them had taught CS2 multiple times. Some of them had taught it 10 to 30 years, right? So people have been teaching this a long time. And we tried to really get a variety of people. So if you look at this chart here, we have 2 people from community colleges, we have 2 from liberal arts institutions, we have 4 from big research schools, and then we have 1 from a public school that focuses on undergraduate education. They're from a range of public and private institutions. They have both small and large class sizes, so we were looking at people who are teaching this to hundreds of students as well as people who are teaching this to 20s of students. So we try to get a wide variety. And then lastly, we see something that's unique to computer science and turns out to be a huge problem for us, which is that these people are all teaching this in different programming languages. So if we look at the variety of programming languages, a lot of them are teaching it in Java, some of them are teaching it in C, C++, and then outside of this particular panel of experts, we also had people who were teaching it in Python as well. So we had 3 to 4 programming languages. If we look across the country, people teach this class in up to maybe 10 different programming languages, some of which are very different from each other. Yeah?
If we're caring about the concepts, do we really care what language they're teaching?
So that depends on the concept, right? And I'll talk a lot about that in just a second. We hoped not. It turns out maybe, right? It's tricky. So when we got into asking our panel of experts what topics were covered in their classes, what we found is something that looks like this. So when you look at this, what you can see, let me see if I can get my pen here, is that we really have kind of 2 batches of classes that are covering different things. We have one set of classes up here that really focuses on object-oriented programming, covers basic data structures, and maybe gets to recursion. We also have one set of classes down here that starts with basic data structures, covers recursion and all of these advanced topics, sorting, algorithm analysis, and advanced data structures, and is really not doing object-oriented programming. We had exactly one class over here that covered all of these topics. However, we have this little footnote here because they assumed that the students already knew object-oriented programming and had like a week of review at the very beginning. So what this kind of told us, we were like, wait, all through the CS community, we've been treating CS2 like there's a single CS2. But when we look at this data, what we actually see is this is 2 different classes that are covering overlapping sets of material. We have one set of classes that is focusing on object-oriented programming, and through that is getting up through basic data structures. We have another set of classes that starts with basic data structures and is really covering this more advanced material and really focusing on things like algorithm analysis. And the other thing we saw when we looked at this is we were, okay, well, the common thread here is really this. We're really seeing basic data structures as the thing that all of these things are covering. We also, when we interviewed or surveyed our panel of experts, we had them rank how important they thought each of these topics were. We had them rank it its importance in sort of 2 different things. First of all, how important students knowing this topic was for them being successful in the course of CS2. The second was how important them knowing these things was for them to go on and be successful in the classes that CS2 was a prerequisite for. And what we see is most teachers think most things are important, but the things that really stand out are object-oriented programming and basic data structures. So at this point, we realized a couple things, one of which was this was way too much material for us to try to develop a single concept inventory for. And the other was, even if we did develop a single concept inventory, if it covered all of these things, we wouldn't be able to give it to any one class, since no one class is really covering all of these things. And at this point, we more or less drastically narrowed our focus. And we said, okay, instead of looking at everything we cover in CS2, instead, let's just focus on this one sub area of CS2, which is basic data structures. And let's really focus on developing a concept inventory for that. And then every CS2 class can test their students on this set of concepts, even if we're not covering every concept that they cover in CS2. And it turns out someone else is developing a recursion concept inventory, so it's really good we didn't do that. So next we needed to figure out, okay, what are our learning goals for this class? And to do this, we surveyed our 10 experts, we developed learning goals based on their responses, and then we kind of repeated this process over and over again. We would show our experts our learning goals, we would refine them. At one point, we had a poster at a CS Ed conference and showed people our learning goals on the poster and had them put up Post-its choosing how important they thought all of these learning goals were for CS2, which was really nice because most people thought they were important. Lastly, we finally met with our expert panel again when experts were only suggesting minor revisions. At that point, we were like, okay, we're looking pretty good. So one thing we saw when we just told people, okay, what are your learning goals for CS2? Were our initial set of learning goals, we had a lot of pairs of learning goals that looked something like this. Like we'd have, you know, okay, I want my students to be able to implement insertion in a list, and I want them to be able to implement insertion in a binary search tree, and I want them to implement insertion in a queue or a stack, right? And we saw the same thing for debugging or algorithm analysis. We had all of these learning goals where they basically looked the same, and we could just swap out the name of the data structure in our learning goal. And so at this point, we said, okay, what we're going to do here is we're going to split kind of what our CI covers into two pieces, right? Because what we're seeing is that many of our learning goals are the same set of skills. Our instructors just want them to be able to be applied to every data structure in this set of data structures. And so we decided to split our coverage into two different pieces. We said, okay, we're going to have a set of learning goals which represent these skills and processes that our instructors want their students to be able to do. And then we're going to have a set of target data structures, and we're going to say, okay, our students should be able to do all of these learning goals to all of these data structures. And I should specifically point out that in our final CI, we don't have like every learning goal for every data structure, because that gave us kind of this exponential blow up. So we cover all of the data structures and all of the learning goals, but it's possible that a student, you know, doesn't understand debugging on a specific data structure, and we could miss that because we're not doing the whole combination. We're just doing both of these things and covering each of them, but in separate categories. So we came up with a set of revised learning goals, and this was really interesting. So these are our first three learning goals. All of our experts agreed that one of these three goals was the most important thing, but they got into a huge fight over which of them was the key thing. And this is really a question of abstraction. So these learning goals here, we have, okay, first, if I'm building an application, I want my students to be able to select which data structure they should use in that application. So should they use a set? Should they use a list, right? Next, we wanted students to be able to, okay, if they're actually implementing a data structure, how are they going to implement it? So if they're implementing, I guess, an abstract data type, which is kind of an abstraction of a data structure. So if I have a list in computer science, I can implement that in different ways that do different things with memory and have different trade-offs. So I can say, okay, I want this to be implemented with an array, which is basically just a chunk of memory that's going to be slow to find things in and slow to grow the array, but it's going to be relatively fast to insert things in. Or I can say I want to do this in a linked list, which is more complicated but has a different set of trade-offs. So they were saying, okay, first of all, I want them to be able to select, which of these high-level types they should use. Then I want them to be able to actually figure out which lower level data structure they should select for an abstract data type. And then after that, I want them to be able to actually design and modify these data structures. So I want them to be able to actually write the code to create these kind of very low level data structures. And
Can I ask a question? So those look like skills to me, with the verbs instead of concepts. Are these skills on the way to, what are the concepts?
So these are skills which the professors wanted their students to be able to apply to the data structures, which would more or less be the concepts. And this is another thing. So we have an outside consultant who is in chemistry, and one of the things we talked about with her was that our set of instructors was really concentrated on skills. And I think a lot of computer science in general is kind of, especially CS1 and CS2, is kind of a skill-based process. And so in fact, all of our learning goals look like this, look like skills, and then they're being applied to the conceptual knowledge of how these data structures work.
That's really helpful, thank you.
Yeah. Any other questions on this? So the interesting thing to me about this is which of these things is the most important is really what level of abstraction you want your students to know. And as computer scientists, we spend a lot of time arguing about abstractions and the appropriate level of abstraction. So them arguing about this was really kind of a fundamental question about what computer science is and what it is to be a computer scientist. So we never solved which one of these was the most important, but we agreed that all three of them were important. And then we had 3 more learning goals. And again, these are really skills, right? So we wanted people to be able to analyze the runtime efficiency of algorithms. This is basically just telling, okay, not only how long will this take, but sort of mathematically what can we say about how long it will take given a different set of inputs. They wanted people to be able to trace through and predict the behavior of algorithms, including code. Code tracing is really a skill that we focus on a lot in computer science. We focus on it a lot in CS1 and going forward to CS2. It's really, if I give you a piece of code, can you read it and pretend to be the computer and tell me what it does? And then lastly, we have this one, which is identify and remedy flaws in a data structure. This is really a debugging question. If I give you code that has a mistake in it, can you figure out how to fix the mistake? And so the interesting thing about both of these learning goals is these are really kind of high-level how to learn to be a computer scientist and write code goals that are being applied to data structures. And so all of these are like, all of these have the word data structure in the goal, but you could take the word data structure out and have a similar learning goal for CS1. And I think that really indicates that one of the things that we are trying to teach students in CS2, even though we're focusing on data structures in particular, is just how to be computer scientists, how to develop code, how to write code, how to tell when your code has a mistake in it. And so then we also had a list of target data structures, which we kind of agreed were the list of data structures which people wanted their students to know are counted as this kind of basic data structure set. And this is where the conceptual knowledge comes in. So our instructors really wanted their students to know how these data structures were defined, know how they behaved, know how to implement them, know their runtime properties, and so on. So now I'm going to talk about some of the problems that we had developing our CI, and specifically what makes computer science a hard problem. And if any of you, all of you are from different disciplines, if this seems like something that you have solved in your discipline, please tell me about it, because I would love to know if you have a solution for this. So as you've seen, several of our learning goals specifically involve either reading or writing code, right? But our students might be learning any of a number of programming languages, and they're going to be, they know how to write their language. If we give them something in another language, they may or may not learn how to do it, or know how to do it, right? So we basically, we looked at what other people had done to get around this. This is obviously a common problem in computer science, especially in these low-level computer science classes, where one of the things we're doing is just teaching people how to write code. And so we basically stole both an idea and a pseudocode from the FCS1 concept inventory, which was developed by Mark Guzdial and some other people at Georgia Tech. It's the concept inventory for CS1. And so we use a pseudocode that abstracts from all of these languages. And we give the students a pseudocode guide that says, okay, here's what our language looks like, and here's how you do all of these different things in our language. So we're kind of expecting them to learn a whole new language to take the test. Mark Guzdial, who developed the FCS1 and developed the pseudocode for the FCS1, we're using his pseudocode. He previously correlated test scores with a version of the test written in a language students are familiar with test scores of the same test in the pseudocode. So we're using a previously validated pseudocode for this. Only 4 of our 13 questions actually use this pseudocode. Anecdotally, I can tell you that when I've interviewed students doing think alouds, they don't seem to be confused by the pseudocode. They seem to get it. Statistically, we don't know yet, right? And I mean, the way we're doing our pseudocode, it's very similar to Java or C or Python or a language like that. If a student was learning a language that worked radically differently, this would look very weird to them. So we're specifically saying we're covering kind of this set of languages that works this way. We're not covering other languages that fundamentally work differently. We also have this problem with naming that we're still trying to figure out. Most of our data structures, so if you look at our list of data structures here, all of these things have one name. If you tell any computer scientist this name, they'll know exactly what you're talking about. For some reason, array lists, which are a particular data structure, have like 50 names. Like, they're literally, when I learned Java, so array list is what they're called in Java. When I learned Java, which was 20 years ago, they were called vectors. In C, they're called vectors. In Python, they're called lists. Sometimes they're called here at UIC, for some reason, we call them resizable arrays. They're also called generalized arrays, dynamic arrays, or growable arrays. So this is something that actually has been a huge problem when we've interviewed, because we give students, we're using the word array list, we give a student a problem that has the word array list in it, and they're like, what the heck is an array list? Like, I've literally never heard of this. We have a set of definitions that we give them with our pseudocode guide that say, like, you may know array list as a vector or a list or a resizable array. Getting students to read a couple pages of front matter before you make them take a test is not something you can necessarily count on. The other problem is that there is a different data structure, which is just called an array, which is not the same as an array list. It's a completely different data structure. And so sometimes students who are not familiar with this array list term may see array list and assume it's an array rather than assuming it's a vector or a list. So this is kind of an open problem we're still dealing with. Another fundamental problem is, again, this problem of abstraction. So different levels of programming languages offer different levels of abstraction from the hardware. So if you're implementing a data structure in C, you're literally working with this is in this place in memory, right? You're literally working with memory addresses. In Python, you are seeing a completely abstracted view that's like a million floors above that, to the point where many C concepts just don't exist in Python anymore. For example, Arrays, which are a fundamental data structure that we learn about in Java and C, don't exist in Python. In Python, we start with array lists. So we actually couldn't assume that anybody who learned Python would know how to implement an array list because that's what they start with and are building everything else on top of. We could assume maybe they know how they behave, but we couldn't expect them to be able to implement them. And likewise, there's a lot of things that the way that you learn to program the data structure may fundamentally be different based on what language you learn to program it in, and how well you understand our questions may also vary depending on what language you learned. So we've kind of erred on the side of making things as abstract as possible. So if you know all the Python concepts, if you learn C, you should know all the Python concepts because they're more abstract and you should know that higher level of abstraction. We're still validating the test, so it may be that everyone who learned it in Python does a lot better than everyone who learned it in C. We just don't know yet. So this is one of the things we're exploring that's kind of an open problem for us. So now I have a couple questions that I'm going to show you from our concept inventory so you can get an idea of what it looks like. So here we have a good example of what our pseudocode looks like. So this is an abstraction from kind of all of our languages. If we were, but it's pretty similar to what things look like in different programming languages. So here we have some front matter where we give them a linked list and linked node class. Here we say, okay, here's a method in the linked list class. We want to be able to add an element to the end of the list. And we specifically tell them, okay, this has a reference to the last node in the list as well as in the front node of the list. So now we want you to fill in this missing code right here. We also kind of give them what they do if the list is empty. What this also does is kind of give them a pretty good example of how we create a new list node, right? Like we're literally saying, okay, we're going to take a variable in here and then we're going to create a node and that's going to look like that. So this should also give them a pretty big hint about what this code is going to look like. So then here we give them that code when we give them a whole list of a whole set of options, all of which are different versions of the sample code that they could do. So all of these are based on student misconceptions. In this version, they're just trying to set these things equal to whatever the node is holding, whatever data the node would be holding. They're not creating a new data structure to hold that. In this one, let me draw you a list and I'll show you. Okay, so the way that we as computer scientists would draw this data structure was we would draw a list that looks like this, and then it's going to hold some elements. So each of these circles would be a node. They would each be holding some data. They would each also have a reference to the node behind them. And then to give us access to the list, we would have a pointer to the head of the list, which is what we have here. We would also have a pointer to the tail of the list. So if we just have one node in the list in this example, we just create a single node, and then we point both the head and the tail to that single node that's going to be holding some piece of data. So here, we create a new list node and we set the tail equal to it. If we did this, we'd have a list that would look something like that, but we wouldn't be updating the tail pointer. So that's just a common student mistake. They don't realize they have to move the tail as well as connecting the new node. Here, we create a new list node, and then we just set tail equal to it, so this is not connected to the rest of the list in any way. This is actually the correct way to do it, where we're saying, okay, tail.next is going to be our new list node, and then we're going to move the pointer to tail. And then lastly, we have this code here, this is actually going to work because what's going to happen is we're going to start at the head, and then we're going to say, okay, as long as there's a next node, keep looking at the next node until you reach the last node, and then set this to the next node. However, this is going to take a lot longer because they're ignoring the fact that it doesn't have a tail pointer. And when I actually interviewed this question, what I saw was a lot of students were like, oh, we're adding to the end of the list, we're going to have a while loop, it's going to look exactly like this. And they were basically just ignoring the fact that they had a tail pointer there. I don't know if it's just because they weren't reading the question or because they actually didn't understand the implication of having a tail pointer. However, I would like you to recall that we had two different learning goals that we're trying to test here. We have one learning goal where we want students to be able to design and modify data structures that are capable of insertion, deletion, search, and related operations. This is really what we're asking students to do here, right? We're asking, if we look at the open-ended version of the question, what we're asking them to do is we're saying, okay, design the insert method for this particular list. However, we have a second data structure, second learning goal, which is trace through and predict the behavior of algorithms, including code designed to implement data structures. And we have a third learning goal that's trace through code and be able to tell if there's a mistake in it. So we have this huge problem, which is on a multiple choice test, all of our questions, which are trying to test our design and modify goal, become questions which are testing our trace through and predict goal. So we really can't separate these two learning goals under our multiple choice scenario. And this is a problem that is common to computer science concept inventories. Some people have opted to not do multiple choice and just create a concept inventory with a rubric. The problem with that is it really limits the practicality, right? If you're asking a teacher to give a exam to, at UIC, our CS2 class has 200 students in it at minimum, right? A professor's a lot more likely to let me give an exam to their class that's multiple choice and give me the results than to say, okay, I'm going to give you this open-ended test and a rubric and I'd like you to grade them all and get back to me. Or even if they're giving me the exams, that's a lot more work for me, right? So in order to make our tests really practical and comparable, we're making it multiple choice, but we're kind of acknowledging the fact that it means that it's almost impossible for us to truly test this learning goal. And we've actually seen this on some of our questions. We have a lot of questions that are testing more or less this goal that students do terribly on in the open-ended question. And once we add the multiple choice version, they're doing a lot better on it. So it turns out it's a lot easier for students to kind of select code that works than to write code that works themselves. So here's another question that I really like. This is getting at kind of how do you test and debug our code. So here we're saying, okay, and this is nice because it doesn't involve our pseudocode, right? We're saying, okay, you have a binary search tree. So this is a classic picture of a binary search tree. You wrote something, a search that finds if an element is in the tree. So if I say, is 40 in this tree, you're going to return true. If I say, is 12 in this tree, you're going to return false, right? So you're not sure if your implementation works or not. Please select 4 integer values that you search for in this tree to gain as much confidence as possible that your search is correct. Okay, so now I'm going to give you guys a couple minutes to stare at this. If anyone thinks they know the answer, tell me.
To embarrass ourselves and guess it?
Yeah.
No clue?
Sure.
Okay. I'll guess E because it's got something from each row of the tree and something that's not in the tree.
Yeah, so that is, so it's actually, which one of these is it? Now I have to figure it out, 20, 30, 40, 50, so E is going to do something that's not in it, and then it's going to do 15, 20, and 30. So that does every row of the tree, but it's only doing
that side.
one side. And so if we look at D, D is doing 25, 30, and 40, and then 50, which is not in the tree. So it's checking all over. But yeah, you did a great job.
What's the answer?
So the answer is D because we're checking, so here, let me erase these so you can see. Here, we're checking 25, 30, 40, and then 50, which is not in the tree. So we're checking every level of the tree, something that's not in the tree, and then we're testing lots of different subtrees. So I really like this one because it really gets at the concept of like how would you test your code, which is something that we want our students to learn, but is actually kind of difficult for us to test. Although students do generally pretty well on this question. And then we have this question. So here we're saying, okay, in a previous linked list, we had a reference to both the head and tail of the list. If we compare this to something that does not have a reference to the tail of the list, so just to the head, in which cases will the singly linked list with the tail do better than the singly linked list without the tail? And the answer is it is either remove the last, no, it's not remove that. It is add a given element to the end of the linked list. So this is really getting at that timing analysis. We're saying depending on, so if we implement a linked list and it looks like this, and we have a pointer to the head, versus if we have a linked list and it has a pointer to both the head and the tail, which of these things will be faster in the version with the tail? And so returning true if the linked list contains a given element. In both of these, we're going to have to look at every node of the list, so they're both going to have the same time. Removing the last element seems like it should be faster. I almost checked it, as you recall, but actually, because we have a singly linked list, which only has pointers one way, in both of these lists, we still have to start at the beginning and go through every element. So that's something that our students get wrong all of the time because it seems like it should be faster, but then this is where the conceptual knowledge really comes in, right? You have to understand how a singly linked list works in order to get this question right. Adding an element to the beginning of the list is going to take the same amount of time. It's adding the element to the end of the list that's going to be faster. And then just my last example here is just to give you an example of something for another learning goal. This really connects to being able to select what data type we should learn in a specific application. So here we're saying you're implementing undo functionality in a program. So you want to save a user's order with the ability to undo them in a reverse order, right? So this is like what happens when you hit Control-Z in a program. And so here we're saying, okay, do you want to add to the end of a singly linked list and remove from the start of it, add to the start and remove from the end, add to the end and remove to the end, or add to the start and remove from the start? And we're specifically saying, okay, with the goal of providing the best performance here. So here, since we want to be able to undo things, right, we want to add and remove from the same end, but because of how singly linked lists work, if we add and remove from the start, it's going to be a lot faster than adding and removing from the end. So that's all I got. I would love to hear from people who are doing work like this in other disciplines, kind of what maybe some other concept inventory problems are, or what concept inventories look like in other areas.